You are currently in Jasmine, and the session you are in is Battle of the SKM and IUM, How Windows 10 Rewrites OS Architecture. And your speaker is Alex Ionescu. Thank you for putting your phone on vibrate in advance. This session will probably take the full allocation, so I don't know if there will be Q&A time here, but Alex has kindly offered to stay around, so if anyone wants to approach him during coffee break, please do. Thank you very much.
Thank you. So welcome to my talk about SKM and IUM, what those words mean, and what the changes are in Windows 10 regarding that. Brief little bio about myself. I'm currently Chief Architect at CrowdStrike, which is a security startup. But most of my OS experience comes from having worked at Apple on the iOS core team, as well as having reverse engineered Windows for pretty much the last 15 years, which led me to be a co-author of the Windows internals books, which are really great sleeping material if you ever have time, problems going to bed. So I like to focus a lot on design issues, design flaws, but also sometimes things that are really well implemented and that don't actually have any of the above, which is what this talk is going to be about. So I'm not going to be dropping any O-days or vulnerabilities. Rather, I'm going to talk about some dramatic, I find, changes to the OS architecture and kind of open up some questions and some thoughts about what that means for the future of platform security. So Microsoft is basically investing a lot of resources into what they call virtualization-based security, or VBS. And Windows 10 and Server 2016 are implementing 3 features to cover that, which are Device Guard, Credential Guard, Virtual TPM, which they take part of a feature called Guarded Fabric or Shielded VM. Now, there's very little documentation so far on a lot of these features. It is slowly starting to come up live. There's a few blog posts. There are a few presentations from Microsoft. And there was a talk yesterday, actually, on Credential Guard. So those of you who attended that talk, Credential Guard does use basically what I'm going to be talking about in this talk. Now, I'm not going to be talking about Device Guard, Credential Guard, or Fabric Guard. Those are things that Microsoft will market themselves. I'm going to talk and go deep into the actual architecture that makes all those features work, which is called Virtual Secure Mode, or VSM. As of last night, there's also a really good talk on Channel 9 on a Going Deep series that also covers some of what I'll be talking about in here. So I have a few references throughout the presentation for those of you that want to go deeper into that. So I'll start with a very brief recap of what those guard features are, and then we're going to take a look at how VSM is architected, how it starts up, and then how SKM and IUM function, both being the kind of the privilege side of the VSM and the user mode side. And then we'll talk about something called TRUSTLETS, how they run, how they execute, and also I'll show you kind of a demo of a third-party TRUSTLET, which is not supported by the architecture, but just to kind of show you what that would look like and how TRUSTLETS are developed. And then we'll wrap up with some kind of thoughts about what this really means and potential avenues of attack or things that could be a little bit better improved in here. So let's talk about some of the new things that are coming up, which you may hear about. One of them is Device Guard. And there's a presentation at RSA about that. So with Device Guard, essentially, as an enterprise, you can now decide what's going to run on your machines using code signing policies and create your own certificates and sign your own binaries and determine what's going to run and what's not going to run. Now, this sounds similar to AppLocker. But what's different is that the signing checks are actually done by a component that's supported through virtualization. So it's not the kernel that's doing the signature checks anymore. It's actually a component through the hypervisor that I'll talk about. Credential Guard, which was presented yesterday here at Black Hat, uses the same virtualization technology, but in this case to actually guard cryptographic secrets. So like your LSAS secrets, for example, your NTLM hash, your Kerberos TGT ticket, those things can now be hidden away. And Guarded Fabric and Virtual TPM is a feature that was talked about at the Ignite conference in Chicago in May, and that has to do with the ability to protect the VM that's running in a fabric provider, for example, in a cloud provider, from the actual host. So you can now have a VM that's encrypted that uses BitLocker, run it on Azure, let's say, and whoever actually owns the virtualization infrastructure can't attack your VM. So you can read about all these features in official Microsoft publications, but I'll talk about kind of what powers all of these things working together. And you can turn all of these on today in Windows 10 through the registry. There's a few registry keys to do that. There's Windows features that you can enable to turn this on, and there's group policy as well. So there's different ways to kind of enable this functionality. But we're here to talk about VSM specifically, Virtual Secure Mode, which is what provides all of this functionality. So how does it all work? Well, as of the new hypervisor that's in Windows 10 and Server 2012, a virtual processor now has an attribute called a VTL, or virtual trust level. Now today there's 2 VTLs. There can be more in the future. And the higher the VTL is, the more privileged you're going to be. And then the nice thing here is, since you're going up, you're not going to end up with those ring -1, ring -2 problems. You can just keep creating higher and higher VTLs. So VTL 0 is what you can call normal world or normal mode. This is where kind of standard code can execute. And VTL 1 is what you can call secure world or secure mode. And it is a more privileged level above VTL 0 provided by the hypervisor. Now these VTLs, they're orthogonal to ring levels. So you can be ring 0, which is kernel mode, in VTL 0. That doesn't give you access over VTL 1 unless you're ring 0 in VTL 1 as well. So you've got your ring levels that are kind of your traditional users and kernel boundaries, but those ring levels are within a VTL, and then horizontally you scale to other VTLs that provide their own ring levels within themselves as well. So now you can kind of think of security as kind of local within a VTL, which is your ring level, and then spreading across VTLs as well. Now this essentially uses what you probably know as SLAT or EPT or NPT, nested page tables, extended page tables, or second level address translation, which is what CPUs that support hardware virtualization allow hypervisors to have their own view of what physical pages correspond, what virtual pages correspond to what physical pages. And you're probably familiar with page table entries, which is where the OS defines this virtual address is readable or writable and points to this physical address. But with a hypervisor, even though the OS thinks that a page exists and is executable, for example, the hypervisor can say, well, actually, no, it doesn't exist, or yes, it exists, but it's not executable. So the hypervisor can basically provide its own additional layer of translation that overrides what the OS thinks. So now you can do interesting things like, for example, blocking read to a page that even the OS can't touch now. And Credential Guard uses that. If I store your secrets in a page that only, let's say, the hypervisor can read, or something at VTL 1 can read, then nothing can read those secrets, even if they're running in ring 0, because they're in ring 0 in VTL 0, not in VTL 1. And so this lets you guard and protect data. You can block execution permissions, which is what Device Guard uses. So you can say, sure, the OS kernel thinks that this page is executable, but when we verify the code integrity through the hypervisor functionality, it did not match the signature that the enterprise wanted, so I'm not actually going to make the page executable in the extended page tables. So the CPU actually won't execute that code, even though the OS thinks it's executable. Or your exploit flips a bit to mark the page executable, that doesn't matter, EPT still say the page isn't. And you can block writes as well. So you can have critical data that even the kernel can't touch because the kernel's running in VTL 0, which is normal world. And so basically by segregating memory access, we can now provide 2 separate privilege levels through the hypervisor. Now the hypervisor doesn't actually implement all of this logic to provide device guard and credential guard and guarded VM. This would make the hypervisor too complex. And we want to keep the complexity of the hypervisor low so that it doesn't have too much kind of surface of attack. Now within Hyper-V, there's something that's called a partition. And typically when you enable Hyper-V, your host OS boots in what's called the root partition, and then your guest VMs have child partitions. Unless you actually boot up other VMs, all you have though is a root partition. Now before, Hyper-V fully trusted the root partition, and the root partition could do everything it wanted through the hypervisor and to everything else. With VSM though, now your root partition first starts out in VTL 1. So you start out in the more privileged mode, in the secure mode. Now code that's running there can then set up the EPT entries as needed, and then we drop down to VTL 0, and everything now runs in VTL 0, which is less privileged. Kind of like your machine starts up in ring 0, and then you lower it down to ring 3. Same thing happens at the hypervisor. So with VSM now, the hypervisor no longer implicitly trusts the root partition. There's this VTL attribute that tells us how privileged you are within that world. So instead of loading your normal kernel and all of its drivers, and Win32k.sys, and all the mess that comes in your usual ring 0 environment, we don't actually load all of NT inside of VTL1 now. So what's actually going to happen is we're going to create two environments of execution. The Secure Kernel Mode environment, or SKM, which runs at ring 0 in VTL1, and the Isolated User Mode environment, which runs at ring 3 in VTL1. So SKM is basically the kernel in VTL1, IUM is the user mode environment at a VTL1. Now the Secure Kernel Mode includes a little kernel, which is called SK, the Secure Kernel, or sometimes you'll see it called the Smart Kernel, the Secure Mode Application Runtime. And it only has two modules, SKCI, which provides code integrity, and CNG, which provides cryptography. There's nothing else. There's no HAL, there's no win32.sys, there's no drivers, and the kernel itself is only about 300 kilobytes. It's not your standard 8 megabyte NT kernel. In isolated user mode, you run what are called trustlets. Trustlets, we're going to see, are little processes that run in VTL1, and they're isolated from each other's, and they're limited in what they can do. When they do system calls, their system calls first go through SKM, through the secure kernel, and then it decides which of those system calls to implement. And we'll see there's a real limited number of system calls that are allowed for trustlets. They don't talk to CSRSS, for example. There's no shimming, there's no app compat engine. And they can only load DLLs that are approved for execution in this environment, and we're going to see how the approval process works. Everything else in VTL0 remains the same. So you've got your NT kernel, NTOS, and it runs through what you can sometimes call the high-level OS, HLOS. Now, it's important to note that the user mode environment is essentially identical across VTL1 and VTL0. So it's the same kernel 32 binary, the same advapu 32 binary, but you are limited in what DLLs you can load. But you don't get a separate user mode environment. In the kernel, though, you do have a separate kernel which is different from the NT kernel. So this is basically what it looks like. You've got your VTLs that are kind of horizontal, and your ring levels that are basically vertical. And you have your binary that's running as a trustlet here, and it's importing the standard Windows DLLs, which talk to the standard Windows kernel 32, which talks to the standard NTDLL. But now those system calls go through the secure kernel, and we're going to see it doesn't implement the system calls. The ones that it does allow you to use, it'll proxy them to NTOS to do them there. On the other hand, you in this environment also will have access to what we're going to see are called secure system calls, which go through a separate DLL, which goes through another DLL, which then goes to the SKM. And these are additional facilities that are provided if you're a trustlet. And we're going to see what some of those facilities are. Now, for this to actually be secure, the bootloader, which is setting all this up, needs to trust the firmware and the platform. Because otherwise, if I boot up when I'm setting all this up, the thing that runs the VTL1 is malicious, well then it's like running malicious code to ring 0, but only worse. So SecureBoot provides this guarantee. Now the hypervisor also needs to trust that you can't use DMA to attack VTL1 pages. Because DMA is direct memory access through physical pages, and it bypasses whatever EPT protections you may have put into place. So we rely on IOMMU or VTD to provide this guarantee that DMA cannot attack us. And the hypervisor also needs to make sure that as it's storing credentials and secrets, it can store them in a safe place and seal them and measure them. And a TPM provides this guarantee. Now with all these three functionalities, SecureBoot, IOMMU, and TPM, you have as a secure root of chain of trust as you can. And VBS kind of requires all of these to be there to provide and guarantee security. Now VSM will work if these are not all there. You can run without SecureBoot. You can run without an IMMU. You can run without a TPM. But then I can't guarantee those things anymore. Now your secrets have to be on disk. Now DMA can attack me. Now bootloader code can be malicious. So really, if these things are not all on, you don't have the same kind of layer of protection. So part of what's running in the secure kernel mode is that secure kernel, but also this SKCI library. And that's your hypervisor-based code integrity, or HVCI. This is kind of an identical-ish version of CI.dll, which runs in VTL0 as part of the normal kernel, and it's what basically checks for certificates, checks for digital signing. And when you enable what are called strong code guarantees through ViceGuard, it's going to be the thing that checks, is this binary allowed to load? That way, even if your kernel is exploited, it's not the exploited kernel that's going to say, yeah, this is allowed to load. You have to exploit SKM, which is a different VTL level, and I need a hypervisor bypass or something like that. And so with the ViceGuard or with strong code guarantees, if you want to run code, SKM has to say, yes, make the page executable. And it's only going to do that if HVCI validates the signature as being valid. Now you can also turn on what are called hard code guarantees. Because the strong code guarantees that come with device guard, they only apply to kernel mode drivers and the kernel itself. With hard code guarantees, you can make user mode behave this way as well. And you can have an enterprise that says any executable, any DLL, and even any PowerShell script that's ever going to run on this machine has to be signed. And SKM will validate if the signature is there or not. And so if someone were to turn this on, well, A, almost nothing would run anymore, but you'd have the most secure Windows environment you could ever dream of. Because everything, including even anonymous executable memory, would have to be signed. And it would be impossible to execute any kind of unsigned code here other than a DMA vulnerability or attacking SecureBoot or going to ring -1 or something like that. So there's a lot of information. So there's a little review. Normal world, secure world, normal mode, secure mode, those are kind of two environments. VSM or smart, that's basically the runtime, the architecture that provides this isolation. And the smart kernel or secure kernel is the kernel that runs inside VTL1 SKM. HLOS is the high level OS, the normal world, and NTOS is the kernel that runs in the normal world. IUM is your isolated user mode, which is your secure world in ring 3. SKM is your secure in ring 0, both of these in VTL1. And the VTLs, again, they're your virtual trust level. VTL 0 is your normal mode, VTL 1 is your secure mode. And VBS is the set of technologies or features that are going to leverage what's there in VSM. So how does this thing start up? Well, it's all done through the bootloader. And so the hypervisor has VSM built into it. And when you launch the hypervisor with the BCD option hypervisor launch type, this will start up the hypervisor, which will kind of initialize the VSM functionality. But nothing will be running at VTL1 yet. When hypervisor is ready to launch, there's a function that's going to basically load a hypervisor loader. The hypervisor loader then initializes the hypervisor, then we drop back down on the bootloader, and now the bootloader runs hypervised as well. Now the hypervised bootloader checks if VSM is turned on and enabled for IUM functionality, which is another BCD variable called VSM launch type. If it is, we're then going to load a secure kernel, which is securekernel.exe. Securekernel.exe imports skci.dll and cng.sys. We load those binaries up, we verify the signatures, and we also basically set up everything that's needed for this. Then we call the secure kernel. So the first thing that's going to load in this environment is the secure kernel, is the bootloader, and then a secure kernel at VTL1. And this is why SecureBoot is critical. Because if the bootloader is compromised in some way, then this whole process can be compromised, and the thing that runs the VTL1 is no longer trusted. But barring SecureBoot vulnerabilities, or you turning off SecureBoot, this whole process is validated through the signature checking that SecureBoot provides. Now, as part of doing that, we're going to check your VSM policy. And that comes from your group policy settings. It's going to come from the registry, essentially. There's this registry key I've got on the slide here, device guard, and that's going to define, should we enable VBS, should we require SecureBoot, should we require an IUM-EXPOSED, and should we use hypervisor-based code integrity. And based on whatever features are set, this is going to be passed on to the hypervisor and through VSM and the secure kernel, which are going to decide what mechanisms to adapt. And so there's a bunch of options that are going to be set as this policy is happening. Now, two interesting options that were not very well documented when I did my research is MSR filtering and NX MMIO. And these are kind of two attacks you could do if you have the hypervisor code integrity turned on. The first one is device mapped memory. Until Windows 10, there was no API to basically get non-executable device mapped memory. So when you called MMIO space, you got executable memory. In Windows 10, they added a feature to basically have the drivers requested to be non-executable. But in Windows 8.1, for example, chances are your video card's frame buffer is actually executable. So if you put code in there, it can run. Now, with the hypervisor and VSM turned on, even if the drivers request those pages to be executable because that was the default, the EPT pages will not be executable. So now your frame buffer won't be executable even though your driver is not updated. The second type of attack is using MSRs, which are model-specific registers on a CPU. And these lets you mess with a TLB and do things like TLB splitting and other kinds of cache pollution attacks and poisoning. Well, Microsoft has a list of MSRs they consider dangerous, and if you try to either read or write them, there's policies that are going to prevent you from doing that, even from the host-based OS. So they actually did a really good job at figuring out what are all the attacks that you could implement and try to mitigate against most of those. So let's take a look at a little bit of the internals of the SKM. So it's very similar to NTOS. It's basically got KE, ETW, RTL, DBG, SC, or usual kind of suspects. But it's also got some specific IUM functions, what are called normal calls, NKs, and it's got its own kind of object manager, its own memory manager, its own process management functions. But these don't actually manage resources. So I'm going to mention a little bit later, these are basically just kind of micro components to provide basic functionality. But a secure kernel doesn't actually have a lot of it doesn't have any resource management and doesn't have a lot of functionality. It's very, very small. It also exports some functions so that cng.sys can load. So things like allocating from the pool are now managed through SKM. Some locking functionalities are provided by the secure kernel as well. Now, if you're familiar with NT, you know there's a PCR at GS0. Well, secure kernel has a structure there as well, which we can call the skPCR. Again, NT has a K thread structure. Well, here we have an SK thread structure. So for every thread that's running in secure mode, there's a structure for that. And every time there's a process running in secure mode, there's a structure for that as well, and we'll call it SK process. Now, unfortunately, unlike the kernel where you have symbols for these structures, there are no symbols, so there's some offsets I put here through reverse engineering, but they might change, and obviously these are not things you're going to be touching anyway, but just to point out there are similar structures that mirror what you have in a normal NT kernel. Now, SKM does provide a few kind of things that are not there in a normal kernel. One of the things is called mailboxes. And mailboxes allow you to basically communicate between IUM and code that's running inside of NTOS. So every process has 8 mailbox slots, and you can fill a slot with up to a page of data. Then on the normal side, there's a kernel API VSL retrieve mailbox, and you can read one of these mailboxes. So it allows a TRUSTLET or an IUM component to basically push some data that can be read from the other side. And we're going to see what uses this. Now, there's also something called capabilities that SKM provides. And capabilities determine which IUM system calls that an IUM component might call are allowed by whom. So there's an allow all policy, a check TRUSTLET ID policy, or a check TRUSTLET instance GUID policy. Every time you launch something in IUM, it has a unique ID, and the capabilities are going to determine which IDs are allowed to make which calls. So basically, they can further log down and say, this TRUSTLET can't do that thing. Now, today, the only thing that uses that are 2 APIs called Secure Storage Get and Secure Storage Put. And the get can only be called by TRUSTLET ID 2, and the put can only be called by TRUSTLET ID 3. And we're going to mention what those TRUSTLETs actually are. So there is some knowledge in SKM about what TRUSTLETs should exist and what are the things they should be doing. Those storage get and those storage put functions, they're associated with what are called storage blobs. And storage blobs essentially allow 2 TRUSTLETs that share a different ID, but a same instance to basically communicate between each others. And we're going to see what storage blobs are actually used for. So mailboxes allow you to communicate from secure to normal. Storage blobs allow 2 TRUSTLETs to basically put and get data in a secured way. Now, what SKM provides are secure mode calls. And secure mode calls are things that are in the secure kernel that NT may need to call. So those are defined by an operation code and a service code. And there's 3 operations possible: resuming a thread, doing a secure service call, or flushing a TLB. And from NTOS, from normal world, you perform a secure call through the VM call instruction. So you basically use the hypervisor hardware extension to basically do this. You put 11 into RCX, and this now takes you in VTL1, and you can do one of those operations. So those service calls are basically things that NTOS needs to query for, NTOS needs SKM to do, or NTOS needs to tell SKM about something. So you can't allocate executable memory with HGCI turned on. So NTOS has to ask SKM, can you please allocate executable memory? And SKM will decide to do that based on the signatures. If you want to load an image in IUM mode, that has to be done by SKM. If you want to flush a TLB, well, now that has to go through SKM as well, because the TLB affects the EPTs as well. Hibernation, crash dump has to go through SKM as well, because now we want to encrypt those pages. So anytime NT needs something from SKM, the secure mode service call is going to let us do that. Now, there's some specialized ones as well. They're kind of interesting. So there is a special call for doing ETW. So you can actually trace from an IUM component, and you can turn tracing on in normal mode and see the traces that are coming from secure mode. Obviously, Microsoft needs a way to actually debug these things. And there's also failure log pages that you can turn on, which gives you some limited information about what could have gone wrong in SKM mode when it tried to load an image, so you can then later on analyze that. So these are kind of debugging features that exist. Now, there's also normal mode calls. Normal mode calls are the opposite of secure mode calls. These are when the secure kernel needs something from NTOS. And again, there's 4 possible operations there. There's normal service calls and normal system calls. And normal system calls are when IUM applications need to do a system call, and we want to implement a system call in a normal kernel, not a secure kernel. And normal service calls are when SKM itself needs something from NTOS. And again, these are done through a VM call instruction. And these take you from VTL1 now to VTL0. You drop down in privilege, and you do the operation that's being asked here. And there's a number of operations like allocating physical pages. See, memory management is still owned by the normal kernel. So when SKM needs some physical pages, it's going to ask the normal kernel to do that. To terminate a thread or a process management, thread scheduling, that's still owned by the normal kernel. So SKM has to ask NTOS to do that. Wait synchronization, copying virtual memory or allocating virtual memory in user mode, debugging, tracing, all those things still have to be done in normal mode, and SKM does a normal mode call to perform any of those actions. The last kind of call that's needed here are EFI runtime calls. Now, when you have an EFI BIOS, there are certain runtime calls that can be called by the OS. So for example, your variables. If you want to set or get an EFI variable, this has to go through EFI. Now for user mode, there are APIs to do this. There's a get firmware environment variable and a set firmware environment variable. Those calls from user mode eventually go into HAL, which eventually calls EFI. But what about a trustlet? What about something that's running in isolated user mode and it wants to touch EFI? Well, VSM can also basically virtualize the EFI runtime calls. Now this means though that when you're doing an EFI runtime call with this turned on, the EFI runtime code will run at VTL1. And this is again why SecureBoot is so important. Because if you don't trust the firmware, now when you're trying to get a variable, the get variable code runs at VTL1 and it now has access to all the pages that normally would be invisible to VTL0. So firmware could attack this. But SecureBoot provides guarantees against that if it's turned on, if it's not buggy. So that's kind of how the kernel side works. Let's look at the user side a little bit, which is IUM. So SKM provides 3 basic services to trustlets that are not available when you're not a trustlet. Secured identification, secured communication, and secure cryptography. These are all provided as system calls, so you do them through a normal syscall instruction. Well, they all have the high bit set. So you probably know the NT calls, they're index 0, index 1, index 2. These calls are 80 million 1, 80 million 2, 80 million 3. And the trustlet basically doesn't do the system calls directly, just like a Windows application doesn't do the system calls directly. There is a base library that implements some APIs. Those APIs then call the low-level library, which is the IUM DLL, and then it does the system calls. Just like a normal application has kernel 32, which then calls NTDLL, which then does the system call, the trustlets work in the same way. And so there's 6 system calls that are provided. These are the indexes for them. So there's a system call to get the identification key and to set your instance. Those are basically to identify yourself or the machine. There's a cryptographic system call, crypto. And then there's the system calls for mailbox and storage, which are part of the communications package. Now the crypto API itself has 5 different sub-calls. So there's 5 different things it can do. The other APIs, you call them and they just do their action. So what can the crypto API do? It can encrypt data, decrypt data. It can decrypt data that's been bound specifically to the machine with the identification key. It can generate a seed, and it can check if we're in FIPS mode or not, since all this is FIPS compliant. But you never have to call these APIs directly if you're writing a trustlet, which you can now anyway. There's another base API that provides that. And so these are the APIs that are kind of provided to trustlets today, which match those system calls, right? So decrypt bound data, encrypt, get FIPS mode, get the identity key, get the seed, post the mailbox, secure storage, get, put, and set your instance. So basically these are kind of the, I don't want to say documented, but the high level interface that trustlets are going to be able to call. Now outside of those specific SKM system calls, you have, obviously trustlets are normal Windows code. So they're going to be calling things like create event, create file, the standard APIs you might have. The standard APIs then are converted to system calls. But SKM only allows you to do 48 of the 2,000 system calls that the kernel has. There's some synchronization APIs that are allowed, semaphores, events, and alerts, which allow critical sections to work in user mode, for example. There's no mutexes. Worker factories, thread API, wait completion packets, which are all used by the thread pool, which in turn allows RPC to work. And ALPC functions are allowed as well, which is required by RPC to work as well. There's some APIs to allocate virtual memory and section objects, which is how you can map a DLL and allocate from the heap. Trustlets obviously need to do that. And there's some random little APIs for exception handling and for querying a few things. But note, for example, there's no registry API in this list. There's no file API in this list. So you can't do any of those things. You can't do registry I/O from a trustlet. You can't do file I/O from a trustlet. You can't do any of the things that are not exposed through a system call that's accessible at VTL1. So if you want to do any of those things, you need an agent. You need something in normal mode that's going to do those things for you. And for example, in the LSAS case, there's LSA ISO, which is the isolated trustlet in VTL1, and there's still LSAS, which is the standard process in VTL0. And how do they communicate? Through RPC. That's why the thread pool and ALPC is implemented and allowed, so that you can communicate across VTLs by using RPC. So there's a lack of functionality you might kind of see there, and that's because trustlets are really designed for the functionality that Microsoft needs: credential guard, device guard, and virtual TPM. Now, whenever you do a system call now, you have a risk, because you have something in VTL1 calling normal mode. What if normal mode's been compromised and it wants to lie to you about the data? It wants to screw up the structures you get back, give you a fake handle, give you a fake buffer. So every time you call into normal mode, you're going to sanitize the output that you get back. When you call into it, though, you have another problem, which is that all your pages now are VTL1 pages. They can't be read necessarily from VTL0. So there's some shared buffers that are used so that I can actually allocate some memory that VTL0 is going to see, marshal structures in those buffers safely, get rid of any pointers to pointers to pointers, and there's some generic marshaling that lets you do that. Then the normal mode sees the marshaled buffers, does the action, returns some data back, the data is sanitized, and then copied back into a buffer that can be accessed by VTL1 can access it anyway. So there's some marshaling and some sanitization that has to happen. And so this is a diagram I stole from Microsoft from a presentation. It is their copyright. I don't make nice diagrams like this. But this basically shows you the whole process. We have the secure kernel trying to do a system call, going through the marshaller, going through VTL0, which then goes in a normal kernel, which then runs a normal kernel function. So all this is now running in a normal mode in VTL0. And then it all goes back at VTL1 now, unmarshal everything, sanitize it or harden it, and return the data back. So the secure kernel doesn't have a lot of functionality. It's almost acting like a proxy, just sending things through to the other side. So how does the trustlet use all this functionality? Well, how do you first of all launch something as a trustlet? In Windows Vista and later, they added something called process attributes. And when you start up a process, you can define some attributes that are associated with it. So one of the attributes you can now set is, I want this thing to launch as a trustlet. Unfortunately, that attribute is not exposed to the standard documented Windows API. It's only exposed to the native API. So you need to build a non-documented application that will acts as a launcher to pass that undocumented feature through the undocumented API. And the attribute you have to specify is a trustlet ID. SKM recognizes that only some things should be trustlets. You need to pass an ID. What trustlet are you trying to execute? When the trustlet executes, we're then going to check, is this binary actually allowed to launch as a trustlet? Because you don't want random stuff to launch as trustlets. And so there's some strong signing guarantees here that are going to make sure that this has what's called a signature level of 12. Now you can read my blog if you want to know more about signature levels, but they're basically cryptographic levels associated with EKUs, enhanced key usages that a cert can have. And so an image that's allowed to run as a trustlet has to have a special certificate with some special key usages in there. One of them that says this is a Windows binary, and one of them that says this is an IUM binary. So it has to come from the Windows team at Microsoft, and it has to be signed with a special cert saying this is allowed to launch as a trustlet. Now, even if you boot in debug mode or in test signing mode, and you make your own fake cert, and you add those EKUs, in test mode or in debug mode, they won't be recognized. So it has to be from a Microsoft certificate, not a test certificate, and it has to have those EKUs. So there's practically no way other than corrupting the system in some way, which requires an exploit, which requires bypassing SecureBoot to actually change its functionality. So only things that are signed as trustlets can run as trustlets. So here's an example of what that would look like. Here are the digital certificate properties of a trustlet, and here it says isolated user mode and Windows system component verification. And you need these two things there. And if you want to run as a protected process, there's another EKU there. But without those two EKUs in a cert from Microsoft, you're not going to be able to launch. Now, when a trustlet launches, it has to have what's called a trustlet policy associated with it. So you have to have a special exported variable. That special exported variable has to have a special name in a special section with a special set of flags. Obviously, it has to be signed because it's part of the binary. And that policy has the trustlet ID. So you can't launch trustlet ID 4 associated with binary X if binary X is signed saying, I'm trustlet ID 8. So the binary kind of signs its own identity, and the launcher of the binary says, I'm launching this binary with this identity. And they have to match. So you can't have arbitrarily trustlets or run a trustlet as a different identity. So all this is checked by the secure kernel to make sure this is a legitimate, valid trustlet. The policy also says, what can the trustlet do? Or what will it allow itself to do? So for example, ETW tracing, the trustlet can say, I don't want my tracing messages to be seen. Dumps, the trustlet can say, when I crash, don't write a crash dump. Or when I crash, I want to crash dump, but encrypt it with this public key, so that only Microsoft, which has a private key, can then encrypt the crash dump. So there's certain policy attributes that the trustlet can say. Another one is allow myself to be debugged or not. So trustlet can say, I do want the debugging facility to be available to normal mode, or no, I don't want normal mode to debug me. And depending on what the trustlet is doing, some of those options are going to be set. LSAS, for example, the isolated LSAS won't allow itself to be debugged. It will allow itself to crash and write a crash dump, but the crash dump will be encrypted with a public key that is specified. A trustlet can also have an instance GUID. That's something used by Hyper-V, because with virtual TPM, you can now have Hyper-V virtual machines that essentially are protected from the host, and that's using trustlets as well. And the instance basically tells you what VM is this trustlet associated with. So what trustlets exist today? Well, trustlet 0 is kind of the secure kernel process itself, which hosts device guard. And when you have these features turned on, you'll see if you look at task manager, there's going to be an entry there called, let me switch this around, secure system. So that is basically an indication that SKM is there. Now I also have credential guard turned on. So I'm going to have an LSA ISO process. This is trustlet ID number 1. And trustlet ID number 2 and 3 are if you use guarded fabric or VTPM. So trustlet 2 is VMSP, which lets you read what's in a TPM. And trustlet ID 3 is the provisioning tool which you would use to put secrets and seal things in a virtual TPM. So those are kind of the 4 trusts that exist today. So LSA ISO provides a credential guard feature you may have heard about yesterday. It only does 2 things, decrypt and encrypt data. That's all it needs, the cryptographic API. The other trustlet, VMSP, is used for virtual TPM. And for virtual TPM, you need a bit of more complexity because now you need to use the mailboxes to basically identify yourself and pass data across normal mode and secure mode without using RPC or by adding another layer of security on top of RPC. And the VTPM data itself, the secrets in TPM, are used with that secure storage facility. So those APIs are kind of specifically designed for VTPM only. The other APIs to encrypt data and encrypt data, those are used by the credential guard feature. Now when a trustlet loads, it gets loaded like any other application in user mode. There's the same NTDLL that you have on the other normal side. The difference is this NTDLL is going to check a few things to basically prevent normal mode from messing with it. So you're probably familiar with the shim engine, which allows you to put application compatibility flags. Well, we don't want LSA ISO to have a shim that says, and go do this. We want this functionality to be non-influenceable by normal mode. So some things are disabled, like image file execution options are ignored, DLL redirection is ignored, there's no communication to CSRSS, there's no shim engine, to basically make sure the trustlet does what it's supposed to do and can't be affected by the admin in some way. Now because you don't talk to CSRSS, there's some structures that are missing as well. So NTDL will basically fake out what CSRSS will normally do. Now since you can't talk to CSRSS though, the key detail here is you can't have a UI, and you can't even have a console. So you don't have access to the command prompt interfaces. There's no standard in or standard out. So you can't link a trust as a console application, because then it's going to try talking to the console driver or the console subsystem, and that's not there. So they have to be linked as Windows images, not as console images. So then how do trustlets talk? Well, they can trace through ETW, which I mentioned. There's a debug print API, and there's local RPC. Now the debug print API is actually not enabled in retail builds, and ETW tracing can be disabled. The trustlet can't say, I don't want to trace myself. So the one thing that trustlets can always do and that's always permitted is RPC. And so there's going to be vulnerabilities here if they're going to be in RPC or ALPC or basically this interface that allows the two things to talk to each other. So if your trustlet is accidentally badly parsing an RPC message, the trustlet can crash. The trustlet may run code that it's not supposed to. Again, though, you have to work around the signing issues and all the other kind of hardening features that the virtualization brings on top of that. But this RPC link is probably where people are going to be looking at. Now, there also is, on top of any RPC kind of server that Trustlet can introduce, there's a special RPC server that's there on normal mode called IUM Trustlet Dump Server. And when a trustlet crashes, if crash dumps are allowed, there's functions in Secure Kernel to talk to the Trustlet dump server and to write a dump out to disk. So this is the one communications channel trustlets always have if they enable crash dumps. They can just shove encrypted data to the server, and the server is going to write it to disk. So technically, you could write to disk with this interface. That's something that's not a dump if you somehow got into a trustlet, but it would be a limited path name and a limited location with a limited extension. So the question is, can you build your own trustlet? This sounds like really cool technology, but it also allows me to basically hide my data if I'm malicious. Can I have a malwarelet? Well, there's a number of things that prevent you from doing this. The first one is you have to have a right policy with the right trustlet ID, with the right name and the right section, and it has to be signed correctly. And those signature checks are not things you can bypass without some sort of ring -1 exploit. You have to be compiled and linked correctly, and you have to be careful what DLLs you use. Not all DLLs are signed with that certificate. Not all DLLs can be used inside the isolated environment. And ultimately, even if you wrote your own malicious trustlet, your trustlet doesn't have access to stuff in normal mode. Everything it has access to has to be through one of those system calls. And a trustlet is protected from other trustlets. So a malicious trustlet can suddenly attack the credential guard trustlet. So you still have to kind of break out from IUM into SKM, and be a pretty complicated attack to do if you got there. And you have to write a trustlet in the first place anyway. But there are ways to do that if there's exploits or vulnerabilities. And so I'm going to do a demo of an actual trustlet, show you how that looks like. And this is my own trustlet, so it's not one that comes from Microsoft. Now, it is a very simple trustlet. It essentially only does two things. It initializes ETW tracing. It prints hello secure world. It creates an event called demolet active to show you that it actually ran. And then it basically sets up RPC and creates an RPC endpoint called demolet port. So I've signed this correctly and everything, and I'm going to try running it. Make sure it's not already active from earlier. Nope. Okay. So I've got my, that's the signing. Okay, so I've got my own launcher, and I've called this trustlet ID 5. It's got a policy that claims it's ID 5. I'm launching it as ID 5. So it says it launched successfully. Now let's see if it's actually in the process list, PID 7200. So there's your trustlet. Now, how do you know this is actually a trustlet, that I'm not lying to you? So let's double click on it. And first of all, you can see that it has created the demolet port. There is an event called demolet active. So if I go inside WinObj in sessions 1 base named objects, there should be an event here, demolet active. So the trustlet was able to create this event. And if I go inside of RPC control, there is the demolet port, so I have an RPC endpoint that I can talk to my trustlet now. But is it actually protected? So let's look at the memory. Well, I can see all of its memory. Well, no, I can see the memory allocations. I can see the VADs, because the kernel owns the memory management, so I can see what allocations exist. But if I try to look at any of these, this is reserved. Let's look at committed region. Invalid access to memory location. Even if I use the kernel debugger, which normally should have all the powers, bang process 00 trustlet.exe. I'm going to attach to it from the kernel, which is ring 0, so I should be able to do anything I want to it. Let's dump the VAD. Let's see the memory allocations. So they're there. This is all trustlet memory. But if I take one of these allocations, try to look at it. Oh, that one worked. Some of these can be shared. So what I probably picked is I'll actually show you if I do a bang peb. Notice that you can see the environment variables there. And that's because part of the PEB is readable and the environment variables are readable. Otherwise, things would just break if you didn't let that. So I probably picked the memory that contains the environment. I just got unlucky. Let me pick a different address. Let's say I'll take this one. It's all question marks. If I take the code itself of the trustlet.exe, let's see that one. It's mapped, dd, 1, 2, 3. The code is there. And that's not something that's necessarily hidden. So images can still be shared, things can still be readable. Other things are not going to be shown, like the heap and the stack. So it's not that everything is isolated. Some things can be shown and readable. But that code is not modifiable, for example. So if I try to modify the Trustlets code from the high-level OS, I won't actually be able to do that. So if I take another thing is, let's say I want to dump the modules. So normally when I do a bang PEB, I should see the loaded DLLs. But notice here that it says null. This isn't really null in the VTL1 side, but in this kind of fake PEB it is. In the real PEB on the other side, the loaded DLLs are here. But I don't actually see that. So I can't kind of investigate anything in this environment. And if I try to debug this or make a dump out of it, it's just not going to work. So this process is basically isolated and protected from me trying to read its secrets or its heap or modify its code that's actually running now. Now I want to be clear, this is not something supported. I had to do a lot of kind of hacks to the system to allow my Trustlet to launch. But just to kind of show you what it provides. Now I can kill it. It's not I didn't make it protected, so I can still kill the Trustlet, and now all these secrets are gone now. So let's talk a little bit about kind of what all this means and what are some of the things that I found out. So first of all, is IUM secure? Is VSM secure? As far as I can see, yes. There are not any design flaws I was able to find. There's no kind of, aha, they didn't think of that. They really did an extremely good job at thinking of all these avenues of attack. Now, could there be RPC parsing vulnerabilities or marshalling bugs? Sure, but it's a very small amount of code. So chances are they took a really good look at that. The attack surface is tiny. The hypervisor is already a very small piece of code. Adding VTLs adds complexity, but it's still manageable. The secure kernel itself is only 350 kilobytes. And yes, SKCI does do ASN.1 parsing of signatures, but that code has been in Microsoft for more than a decade. It's been very well tested, and it's not a full ASN.1 parser. It's a very limited one, which actually is a static state machine. So this is all provably almost correct code that should have very, very little attack surface. On the flip side, though, this does rely on platform features to work and to be well implemented. Now, it's important to point out, which I've mentioned a few times as well, that a secure kernel is very simple. It doesn't do scheduling. It doesn't do memory management. All the resource management is still done by the normal kernel. There's no hardware drivers. There's no devices. And system calls are proxied through normal mode. There's no implementation for system calls in SKM itself. So SKM doesn't trust NTOS. It does depend on it, though. So could you decide, nope, I'm not going to give you that physical page? Sure, and you could screw with SKM this way. So you could do denial of service attacks, but it doesn't give you access to the secrets and the information that's inside the secure world. You also can't NOP out calls. Sometimes someone asks me, well, with device guard, what if I just don't ask secure mode to, is this signed or not? What if I just lie and I tell NTOS, yes, this is signed? You could lie to NTOS and say, yes, this is signed. But then the EPTs, are they going to be executable? No. So NTOS is going to think this is executable memory, but no one made them executable. Because you knocked out the call that's going to make them executable. If you don't knock out the call, then we're also going to verify the signatures. So there's no way to, you can bypass communicating to the SKM, but then you don't get any of the features or needs that the SKM has. So how would you compromise this? Well, again, the reliance, one of the weaknesses is the reliance on SecureBoot, and also the fact that not everyone has an IUM-EXPOSED. And so at Black Hat and other conferences, there's been lots of talks about vendor bugs, design bugs, flash bugs, option ROM bugs, and other vulnerabilities in firmware. And this is kind of the weak spot today. And Microsoft is doing a lot of vendor kind of punching to make sure people get their bugs fixed. Windows Update can also now deliver BIOS updates as well, but this is the weakness. The other one is DMA attacks. Not everyone has an IUM-EXPOSED, not everyone turns it on. And so with those attack venues, VSM can be compromised. Now, kind of the risk here is a compromised VSM can then be used against the user itself. Because now it can use the VSM facilities to hide malicious data. But this is kind of a very limited risk. Because remember, you still don't have access to the file system. You don't have access to drivers. You don't have access to registry. So if you really wanted to run a malwarelet, you have to have an agent that's a malware agent too. And that's something running in normal mode that I can detect. So yes, you could use this. You can use a compromised VSM to hide data, but you could have built your own hypervisor anyway if SecureBoot is not there. So it's not a VSM vulnerability. It's just something a VSM might make easier if it gets compromised. But if it's compromised, it's game over anyway. So these are kind of very fringe types of attacks. So the real issue is if you don't have SecureBoot. If you don't have SecureBoot, then you can bypass all of this. So for example, my laptop has a special version of SKCI where I made a 1-byte patch. With that 1-byte patch, I'm able to reload any trustlet that I want. And so there's a DMA attack, if there's a SecureBoot attack, and you patch that 1 line or that 1 byte, then now you can run your own trustlets. Again, that doesn't necessarily mean it's game over because the trustlets still need a way to do malicious things. So it's really important to make sure that all these platform features are turned on. Now given that, there are a few things Microsoft could probably do to make it harder to do what I did. For example, if SKCI validated itself. If the hypervisor had some code to make sure that I didn't patch it. Something like PatchGuard basically, but in the hypervisor, that could allow you to kind of detect some things that are going on. All these would be defense in depth though, right? Because if SecureBoot is not working right, you can't really protect the system in a true secure way. But there could be little things that they do to make it harder, to make the attack less than just let's flip a byte. Just like in kernel mode, there's PatchGuard, and if you flip a byte, you'll eventually crash the system. So these are lightweight recommendations. They're not really major things that affect the secure system. It is designed to be secure, but your platform has to be secure as well. So with that, don't know if I'll have time for questions. Like I mentioned, though, I will be available at the coffee break. And I also want to thank a few people from Microsoft that helped out a lot with this presentation, making sure it was accurate. So kudos to all those people. So thank you.